So the idea is, normally this is very unstable, but it's just keeping it standing upright. In theory, you can drive it around as well, but this doesn't often work. You can also give a bit of a push and it will...
Because push is involved.
Yeah. Very much so.
That is freaking awesome.
So it will fall over eventually. So
that's a big packet double A action. There's a fair amount of weight at the top of that.
Yeah, and it needs that, because that's how it works. So there's a few other examples of self-balancing robots you might see, like the hoverboards that you can find, or maybe a Segway. And now Boston Dynamics has got these ones that can drive around in doing warehouses, picking stuff up and getting in tight spaces. So there are some uses for them. It's not just toys like mine or the one in the middle. And it's all based on the idea of pendulums. So try not to use the last one. So the difference between a pendulum, a normal pendulum is something where you have a weight and a pivot point, and it's really stable because whenever you let go, gravity always pulls it downwards, whereas an inverted pendulum is the other way around. You have a pivot at the bottom and weight at the top, and it actually works better if you have more weight, and it's always trying to fall over. So the idea of systems like this is you're always trying to catch it from falling over. So you have to constantly adjust, and the idea is to keep the pivot point underneath the centre of gravity, the centre of the weight, and that will be stable, but it's constantly changing, so you always have to adapt to that. And this has actually been used in rockets as well, because they're also an inverted pendulum problem. But the first guy to make proper liquid rockets was this guy, Robert Goddard, and he got confused as well. He actually put the rockets at the top because he thought of that like a pendulum and keep it stable on the way up. It doesn't do that though, because everything's connected. So gravity is actually pulling on everything, and it's not a fixed pivot, so everything is kind of free fall. And that's why rockets have the system where they're constantly correcting to keep this stable inverted pendulum motion. So the simplest way, and the system this uses, is to use a thing called a PID controller, which stands for proportional integral derivative. And you've basically got these three components, you add them together, and then you drive an object, and you go around in a loop. So over here, this is measuring whatever quantity it is, sending it through the system and going around again, just trying to, you have your value coming in from your sensors, and you have the set point, which is the point we're trying to reach. And the system tries to get one to the other.
Is it possible to let us know what each of the symbol?
I'll get into that. So a bit of the history. Most of this first uses something a bit like this was a torpedo in 1866, but it was very much hacked together and nobody done the science behind it. And then in the 1910s, the first practical system was from Ozberry for large ships, and this is non-digital, so this is actually using things like this, which I think this one's pneumatic, or we can get hydraulic. And the guy who sort of formalised all the Massner things, this Nicholas Minorski, 1922, who was doing experiments with large battleships and trying to get them to be easier to sail. And I think the helmsman at the time didn't like all this newfangled technology, but it did actually steer it better than that.
involved in the brake ships with the ballast, auto ballast control?
Yeah, it's used in all sorts of areas. So, a few examples, like large ships. Water level is one of them. So you just have a water level sensor and a pump, and you get it to try and keep the same level. It's used a lot in heating and cooling, things like air conditioners and furnaces that try and keep a constant temperature, pressure as well. And there's lots of industrial uses like CNC machines and routers and lathes and things where you need a constant rotation. So you have a sensor and a motor, and you use the system to try and keep it at a certain level. And of course, there's things like self-balancing robots, but they all. And the other one that you might have thought about before is cruise control in a car, because that's trying to make sure that you're going at constant speed, no matter if you're going up a hill or downhill. It takes that into account. So the proportional gain is the easy one, the key part of the system. So all of these work on working out the error. So you've got your value coming in from your sensor. In our case, it's the angle that the gyroscope's telling us we're at. And you've got the set point, which is where you want it to be. So you take one from the other, you get a difference, and that's called the error. And normally we have this extra P gain in here, because usually your motors don't take an angle. So there's some factor of the whole system that you just multiply it by, and you just have to fiddle with that. There are some auto tuners, but often you just fiddle with it manually to try and balance it correctly. And this will get you quite a long way towards getting to your set point. So this is an example. In blue here, we've got our set point set to 2 and starting off at 0. So over each time sample, we work out error, which is this orange line. It starts off really high. It's 2 minus 0 is obviously 2. So we start moving towards it, but because we're talking about mechanical systems, nothing is immediate. You have inertia, friction, all sorts of things slowing you down. So over time we're going to start moving towards that. You can see as we go, we get closer to our value and the error comes down. You can see there's a bump at the top here, and that's, again, because it's mechanical, there's inertia, it's going to overshoot a bit, and then come back down and settle out. And that's mirrored in the area down here. And we can account for that a bit by using the differential. Now, I've done any calculus. This is calculus, but it's a simple calculus. So the differential is basically the slope of this error as it's changing. And the bit that confused me was I was always thinking about the value, but all of these things you have to think about the error. So that orange line that's coming down. So if you look at the slope of this, you can see it's a really steep slope to start with, and then it peters off. And also, as it's coming down, it's negative. So that means this differential acts as a bit of a brake to slow you down. So as you get closer, it's saying you're going really fast, you need to slow down, and that is the reason that we don't fly off the end. It actually smooths out the curve a bit. So to compute this, we need to work out the slope. So we need to know the last error and the current error. We just take away the difference of that divided by whatever time step we're doing. If you get smaller time steps, then you get much better results. So if you can do it as quickly as you can, you get a better estimate for the differential. And again, just multiply this by some value, which depends completely on the system, and add that in. So we've got our proportional giving us the main change. We've got a differential that slows us down a bit. And here's a massive differential. You notice it's rather large values, so our gain for this tends to be quite small to bring it back down again. So I think this one is set to about, I think it's 1.5. I think the proportional's set much higher, something like 70. And the next one, the I, is the integral. For lots of these things, this one's a bit optional. But what this one does, it takes account of any error over time. Well, any sort of accumulated error over time. So as you're running, you keep adding up all the error results. And if it's still increasing, then you can use that to bring it back down to the value that you need. And this can take account of things like friction or wind or initial starting things, or things being out of a line. And also sometimes as your proportional control gets closer to the value, it's going to be giving you less and less force to bring you to that set point. But sometimes it's not enough. So this integral can also just push it up to the set point. So this one, you'll notice, is really, really small numbers, because usually we're not that far off. So this one, I think, it's set to something like 50 to 100, that sort of range, but again, it's all going to depend on whatever system you're doing. There's no sort of set numbers, there's a sort of general range you can think about. I didn't draw this on the same scale, because otherwise it would basically just be a straight line compared to everything else. So you add these all together and you get your compensation signal that you then send to your motors. Yeah, it depends on your system. I cheated a bit, and there's a really good Arduino library for PID, so I didn't do it myself. And it also really likes it if you can keep the step size the same. So rather than putting it into a loop and just having a delay, you've actually got, it goes into the loop, but it checks how long it's been between each loop. And if it's that step size, then it goes and computes everything. Otherwise, it waits until it needs to go on. And that's a bit more accurate than just saying, wait 1 second, wait seconds, or whatever. And then you get much closer fit to the run. So my robot, as you saw earlier, is this one. It started off originally looking like this, which was a kit from J-Car. And that kit was all about dodging walls. So putting it together, it was an Arduino with a distance sensor on the front, and there was some sample code that came with it. So it said if it came near a wall, turn away, drive off, turn away. My son actually used this for one of his technology projects with COVID, and couldn't go into the school. So it's had a few uses, got a bit of money's worth out of it. I think they've actually updated it now, so it looks quite different, but it's probably a bit better now. The sensors that I'm using, main one is this board here, which has got these 3 sensors on it. The main one that it's using is the gyroscope, which senses change in angle. It's also got an accelerometer, which tells you how fast you're going in a straight line with X, Y, and Z. It's also got a temperature sensor on it. I think it's got a magnetometer on it as well, but I haven't used that yet. So in theory, it's a 9 degree of freedom. So we can combine 3 accelerometer axes, 3 gyroscope axes, and 3 magnetic axes. So this is known as a MEMS sensor, which is a microelectrical mechanical. And these are the sort of sensors you get in your phone. And they're cheap, easy to use, there's lots of libraries for them. And they're called micromechanical because they do actually use not just electrical, but they actually have mechanical parts moving inside them. So I think this is the actual layout of this chip, and it's got these weights which are constantly moving. This is for the gyroscope. And when you get movement, you get there's this Coriolis effect which gets applied at 90 degrees to the movement of the weight. So depending on how it's moving, these jiggle in different directions, and you can then pick that up with a piezoelectric crystal which changes the resistance, and you can read that off. So there's 3 different axes that this one uses. All of these sensors, because they're in the real world, they all have noise. So that's why it's got this step at the beginning where I go through, I think it's about 1,000 steps just to work out an average value, and then we can use that as our 0 value. These also drift over time, especially the gyroscopes. So the gyroscope doesn't actually measure angle, it measures how quickly the angle is changing. So to get the actual angle, you have to have a starting point, and then you add on to it how fast you're moving, and you keep doing that. But it drifts over time, so it changes a bit. So the way to compensate for that is you can use other sensors. And we got these other ones, but they've all got their own downsides. So an accelerometer is the one that's normally used because we can work out an angle by seeing what force is on it. And normally these work, and they work really well with things like quadcopters, by sensing gravity, because they say gravity is going downwards, I know that direction, I can work out. If I know what angle the main force is, it's going to have to be gravity. And you can work out the orientation of everything else. That doesn't work on something like this, which is jiggling all over the place. It can't work out the difference between gravity and the movement. So I did try using an accelerometer. It was terrible. It's a lot worse than just relying on the gyroscope. And I've also got a magnetic sensor, which I haven't used yet. But I've heard they're a bit fiddly. And also, if you've got lots of electronics near it, then that's going to be generating magnetic fields. So it can be a little unreliable as well. But maybe it was helpful. And the one I ended up using on the back here, it's an ultrasonic sensor. So it just works out the distance. As was explained earlier, you just send out a pulse of ultrasound, listen for it, you can work out the distance, speed over time, and the speed of sound. And that recalibrates. So as it's coming up to get to the set position is where we turn everything on and we take a note of the distance to the ground. And whenever we start falling and we notice it's the same distance, we can say this is the angle. So that compensates for drift a bit, but it also means this can't climb hills. Because if you had a great big hill here, then it wouldn't think it's closer than it really is, and it would fall over again. So there's pluses and minuses, and this one is just held together by blue tack, so that's another problem. So it's possible to get a lot more accurate. Moses. So here's some examples of ones. Accurately, this is actually the one I'm using. So I think at the last Ozberry meeting there was an explanation of H bridges. This is the upgraded version of the one I'm using. So I think this is an LM298. It's very popular, very easy to obtain, very easy to use. So H-bridge does two things. First thing, it amplifies the signal because these motors just can't run on the 5 volts the Arduino supply. So the signal you supply to it then switches I can't remember how many volts it is, but it's a lot more volts. I think it's 9 volts. It then goes to the DC motors. And the other thing it does is it's got this H bridge which lets you change between backwards and forwards. So it's called a H bridge because it looks a bit like a H with a motor in the middle, and it's got these 2 sets of switches. So depending on which switches are connected, the power goes through one way or the other on the DC motor. The polarity just means that you rotate one way or the other.
Tell them what happens if you turn all the switches on at once.
Then you short the power supply out and you get lots of smoke. Never let the magic smoke in. And I think these ones do have protection against that. I haven't tried it though, so I recommend that. Try it. And as was mentioned before, it uses pulse width modulation to control the speed of it. So it's got a pulse of signals. I don't think the actual speed matters. The actual speed of the pulses matters. But the thing that does matter is the duty cycle. So that's the proportion of how long it is on to how long it is off. So if you've got 100%, then essentially you've got a full signal. It never stops. But halfway you're turning it off half the time, turning it off half the time. 0 essentially, well, 0 is nothing, and then you can have any value in between. I think in this case it's an 8-bit signal, so you've got 256 levels that you can choose from. And you just tell the PWM library, this is my output range, give me some number between that. Choice of motors. This is the one I am using, which is a cheap 12-volt DC brushed motor. Lots of people use stepper motors, a bit like this one, which they have the advantage that you can tell it exactly how many steps you want it to rotate. But they also use a lot more power. If you're relying on batteries, they don't last as long. There's other things in between. You can get brushless motors, which have a lot more torque. You can also get encoders, which tell you how fast the motor's moving. But in this case, it doesn't actually move them. And this has actually been the hardest bit to try and get working. It still isn't working. But because I'm using an Arduino Uno, it doesn't have any Bluetooth or wireless. So I had to connect a second microcontroller to it. And there's a library, this BLE gamepad. I think there's another one called BluePad, which if you use it like you install it as a board in the Arduino IDE, and it handles all the Bluetooth connections for you. It supports lots of different controllers. So my son happens to have an Xbox. We've got a few Xbox controllers, but it does PlayStation, it does quite a few different things. And it's got quite a nice example code. And I was expecting that to be the easy part, and it's still not working. it. And they talk to each other. So they're connected, their serial ports, serial pins are connected together. And actually, I'm not using the default serial pins on the Arduino because I need those for USB to be able to upload programs to it. So it's using software serial, which is assigning 2 other pins for transmit and receive. And then connect into the receive and transmit on the ESP32 and talk to each other. And because I like punishing myself, I thought I'd try and speed it up and make it a binary connection rather than sending text. And that's when I found out 32 in ESP32 means it's got 32-bit integers. The Arduino doesn't. It's got 16-bit integers. And the first time I found that out was when I just got this garbled rubbish. So you actually have to specify specifically, I want 16-bit integers from one to the other. And then I found it was even more garbage because it was sending this stream of data and receiving it, didn't know where the start was, so it was receiving half of it. So then you have to add a header onto it. But it is working, and I think it's a bit quicker than reading text. But whether it was worth it, I don't know.
We patented your own protocol.
Yeah, basically. If I wanted to be really crazy, I could have sort of footer as well, but that's a bit much. So in theory, the remote control, you're just changing it to go forwards and backwards. You have your middle position where you're balancing. If you want to go forwards, you should just lean a bit forwards, and the whole system will try and keep up with it. But so you're being a bit cruel because it never will be able to reach that point. And the same for backwards. And it does try to do that, but something's gone wrong somewhere in the system, and it just doesn't like it. There are commercial versions that do work. And going left and right is even easier. So on top of the self-balancing, you just need to make one wheel go faster than the other, and you'll turn one way, and you can do it the other way. Alternatively, you can make that includes if you have one going backwards and one going forwards, then you can turn on the spot. Future improvements, as I said to a few people, there's another gyroscope called the NPU 6050, which is useful. There's a lot more examples of it, and there's good reasons for that. It's got some libraries that can combine the gyroscope and the accelerometer for you, and it's done by somebody who knows what they're doing, so it actually works. I think it also can use IRQ interrupts, so it tells you when there's a new sample available. And if you're doing anything with gyroscopes, I'd recommend going for that one, not the one I went for. Stepper motors, arguably, might be better. Using onboard Wi-Fi would have made it a lot simpler because I just need one board to handle everything. But this is what I had. Although it's quite fun working out how to get them to talk to each other anyway. And yeah, Bluetooth. Bluetooth holds things together fairly well, but there are stronger systems. So I may upgrade it to hot glue at some time. And I do have the code available for this. So there's, I think I've got 3 things. I've got the code to create the example graphs. I've got the robot controller itself, and then the remote control. I can actually show you that. So yeah, it's all on this page. If you want to look. Any questions?
How much time have you invested in this project?
A little bit.
Was this a COVID project or?
I don't know, maybe it's been about a year or 2, something like that. but it's just been incrementally adding things onto it. So I actually started off thinking I wanted to do an inverted pendulum because it sounded fun. I thought I could have a stick that it would hold up and just move sideways. Then I thought that's boring. And then I thought, originally these wheels were slightly down here, and I thought just move them to the end and then it could stand up and it got much forward. Yeah, I think the first one of these I came to, I had it balancing, but adding the remote control has been at least 6 months. It's still not working. It probably never will work, to be honest. But it's been fun to try and work it out. And I thought that would be the easy part, just be.
Yeah, I find almost every project I've worked on, the stuff he thinks it's going to be simple, it's the opposite.
Yeah. Actually, that was the boring one. That's the remote control. So the actual code is here, and it's doing quite a bit. Now this is a bit that I put in to combine the code together. So in theory what you do is you take 90% of the gyroscope and add in a bit of the accelerometer. It never worked. Well, it worked, but it didn't give good results.
Do you know whether your code would work with someone with slightly different hardware setups? As in, like if you have battery in different locations?
If you have the same sensors and everything, it probably would work. You'd need to change PID controls. So those are defined up here. So these are my constants. So we've got 18 for the P gain, 100 for the I gain, and 0.3 for the D gain. But all of those were worked out just by trial and error, just changing them. And I did actually that's one thing this control was fairly useful for, because I set it up so that you could press the buttons and in real time change the PI and D.
That's cool.
So you didn't have to write them down, recompile, upload, try it again. Which I did the first time, and that was a right pain. That took weeks to get going. But you get close, and you're never quite sure if you put it exact, but it's the case of getting it good enough. And there is an auto-tune library as well, but I don't know if it would work on something that's changing as quickly as this. Maybe if you're doing something like, I think it's been used for when you've got components, you need a soldering oven to heat stuff up. I think it's used quite a bit on that, just to keep constant temperature, and that sort of thing you could auto-tune quite easily. But this, I think it would just fall over before it auto-tuned. But I haven't tried it, it might work. So, yeah.
Do you think the thing that you're sticking, the blue tack, is that what you said?
Yeah.
Is that would the dynamics of that actually change the PID
It will
values?
be,
Yeah. Okay.
Especially if you're sticking it back on again.
Yeah.
Slightly different position or orientation. Or it's slipping. And dealing with all the different errors has been the hardest bit. There's things like the motors, although they're the same motor, they've got slightly different properties. So one might go slightly faster than another one. The gearbox might be slightly different, there may be slightly different coils or quality in the copper. So you can compensate for that. And in fact, if you want to get really fancy, what you can do is get motors with encoders on them and have a second PID controller to get them in sync with each other. So you set one rotation as a set point for the other one, and basically have master-slave relationship. And people have done that before. But dealing with the gyroscope is the trickiest part. And I think the only way really to get around that is just to get your loops as fast as possible and just compensate as much as you can. So it's been a fun project, that's for sure.
Atmospherics would play a role in it too, wouldn't it? Like just the ambient temperature alone would offset. Not so much.
Not so much, but I suppose it's possible it could affect some of the mechanics. Yeah.
Get it warm enough, it's just oozes down.
Yeah, things start melting. That's pretty bad. And I think if this was bigger, it might be easier to control as well, because you've got something that's much heavier, and the inertia is going to be bigger, so it's going to take longer to change its speed. So going smaller is actually a bit of a problem.
Oh, are you saying the bigger it is, the more less angle it's going to change over?
Yeah.
Yeah, I see.
So it's going to take more force, but that force is going to take a lot more time to either start or stop.
Really cool.
I've got a few other ideas for projects, but this is the current one, and I wanted to just talk about it before I might need to strip it for parts.
Proof you did do it.